Okay, good morning, everyone. Thank you for joining this session on LLM-powered recommender systems. Today, we are going to explore how large language models are transforming the way we build recommender systems. And we'll get on a hands-on experience building a hybrid recommender system that combines the best of both worlds, the efficiency of traditional vector search with the intelligence of modern LLMs. By the end of this session, you'll have a working movie recommender system running in a Google Colab notebook that can explain its recommendations in natural language as well. Let's dive in. A bit about me. I'm Sheetal Borar, currently a senior applied scientist at Etsy, where I work on recommendation ranking, personalization, and building ML systems that serve millions of users every day. I've spent my career across different domains from e-commerce at Amazon and Etsy to finance at JP Morgan and Deutsche Bank. But the common thread has been using machine learning to help people discover what they're looking for, even when they don't know what that is quite yet. What excites me about this space right now is how LLMs are opening up entirely new possibilities for recommender systems, not just in terms of accuracy, but in terms of explainability and personalization as well. And that's exactly what we are here to explore today. I'm also very happy to have Gayatri Ramanathan with us here. She's a senior data scientist at CVS and will be helping answer questions throughout the session. Please don't hesitate to raise your hand or reach out to us if anything isn't clear or if you're struggling with any specific topic. We are here to help. Okay, first things first. I want all of us to get started with setting up our OpenAI API key. This is a crucial first step. You will be needing this in the tutorial. So first we can go to, I think I'll have to do this here. First, let's go to this link. How do I share this to you guys? You can go to platform.openai.com. And then in the settings, organizations, there is an API key link. Yeah, we are going to try to share the slides in a minute. But until then, please go to this link, platform.openai.com, settings, organizations, API key. You can go here to create a new key, put a name for it, like PyData, Boston, something like that. Then you can select a project as a default project. Once you have done that, you can click on Create Secret Key. The key will be presented to you at that point of time. Please make sure to copy that to your notepad because you're going to be needing that key during the tutorial. So go ahead and copy that over. And yeah, I'll do like a show of hands when people feel like they have.
Give us a second.
Yes.
This might be a surprise, but not everybody already has an OpenAI account.
Yeah, sorry. Yeah, go ahead. You create your account and then you can create your key. Once you have created your API key, if you could go to the billing section, add some small balance to your account to actually make inference calls to the OpenAI interface. You could just like add some small credit balance to it.
It won't work without it?
Yeah, no, they need some small balance, like not much. You can follow through most of the tutorial without needing to make inference calls, but this is LLM-powered recommender system, so to use the LLM, then we would need a little bit of balance, yes. Okay, so if you also go to the conference schedule, you should also be able to access the slides and the notebook link through that. That might be easier than doing it through the Slack channel, I think. Yeah, so if you just go to PyData Boston, go to schedule, you should be able to see it there. I'll just copy the slides there too. Before we dive into the technical details, and now that we have done most of the setup that's needed for this tutorial, Let's ground ourselves into why recommender systems matter in the first place. Think about the last time you opened Netflix, Spotify, or any e-commerce site. You were probably faced with thousands, sometimes millions of options. How do you even begin to choose? That's where recommender systems come in. They serve three critical functions. They help users navigate massive catalogs. At Etsy, we have over 100 million active listings. Nobody can actually browse that, so recommender systems help you surface relevant items from this ocean of choices. They reduce decision fatigue. Too many choices actually paralyzes us. Good recommendations filter down what matters, making decisions easier and faster. They improve engagement and satisfaction. When users find what they love quickly, they are happier, they stay longer, and they come back more often to the website. The ultimate goal is to connect people with items, content, or experiences they love. This is not just a business goal, it's a genuine service to people trying to navigate an overwhelmingly digital world. Now, let's talk about how these systems actually work. Let me walk you through two classic approaches of building recommender systems. They're fundamentally different in how they think about recommendations. So the first one is collaborative filtering. The key insight here is very simple. Look at what similar users have liked. Here's how it works. We have two users. Let's call them the purple user and the blue user. Both of them have read two articles at the top because they share similar reading behavior, and hence we consider them similar users. Now, the purple user has also read this article at the bottom, and the system says, hey, these two users have similar tastes. The purple user liked this article, so let's recommend it also to the blue user. The magic of collaborative filtering is it requires no understanding of the content itself. We don't need to know what these articles are about. We just look at the behavioral patterns, the wisdom of the crowds. The second one is content-based filtering. Now, content-based filtering takes a completely different approach. It says forget about what other users did. Let's look at what you specifically liked and let's find you similar content to that. So here we have one user who read this red article. The system analyzes the content. What is it about? What is the genre? What are the topics? Then it finds similar articles shown in green. And based on the content features like the keywords or the category or semantic similarity, it's going to recommend this to this user. The recommendation happens because of the direct relationship between the items themselves, not the user behavior. So the fundamental difference between collaborative filtering and content-based filtering is collaborative filtering says people like you also liked, and content-based filtering says because you liked X, you might like Y. In practice, modern systems often use both approaches, and they call it hybrid filtering. These classic approaches look straightforward in theory, but implementing them in industry comes with its own challenges, which is what we are going to get into now. So here's where theory meets reality. Classic collaborative filtering faces a fundamental scalability problem. Think about it. User to user similarity requires computing similarity between every pair of user that a website has. Item to item similarity requires computing similarity between every pair of item. Let's do the math. If you have 10 million users, and if you have 10 million users, that would be 10 million into 10 million, that's 100 trillion. And if you have similar scale of items, that is same number of computations that you would need to do. Even with clever optimizations, this becomes computationally prohibitive. For example, at Etsy scale, we have hundreds of millions of users and items, and this, like, just actually comparing the similarity between users or between items is not scalable at all. The memory requirements would explode, the computation time becomes unreasonable, and updating the model in real time, we just can't do it. It's not possible. There are other problems too. Cold start problem, there is sparsity in the data as well, and diversity is also something that these systems would struggle with in theory. Hence, I think this is the kind of approach that we have decided mostly in the industry. This is the standard approach in which recommender systems are built in production nowadays in companies like Etsy, Netflix, YouTube, and Amazon. It's a two-stage architecture that separates concerns beautifully. You notice the vertical line in the middle labeled online and offline. This is crucial. Let me walk you through each stage and what exactly happens. So the first stage is we train an embedding model. We use historical training data to learn how to convert items that we have available into vectors. This happens periodically, maybe daily or weekly. Then we embed items from catalog. Um, we use this embedding model to embed the items from our catalog. We run every item through our training model. We create vector embeddings for millions of items. And then we build an approximate nearest neighbor index. This is computationally expensive, so we have to do it offline. This is also done periodically. Then other offline steps for ranking are we pre-compute the features that we would be needing for ranking. We use hundreds and thousands of features. So computing them or doing the feature pre-processing for them in real time is going to be prohibitive, and it's going to add a lot of latency to the system. So instead of doing that online, we will do that offline. And then we will train the ranking model using historical interaction data. All this heavy lifting happens offline, so when the user comes to our site, we don't want to do this because all this is too slow to do in an online manner. Now we go on to the online flow. This happens in real time when you make the request. First, the retrieval stage, we embed the input item or the user. So if we don't have, for example, if you're on a listing page, let's say on Amazon, you're on a page for an item, then you would be embedding the item itself. If you're on a general home page or something and you're not tied to any item at that point of time, we would be embedding the user itself because we have more information about the user at that point. So we would the user searches for something, we use their history, convert their query or profile to an embedding vector because we have already created an embedding for all the users and all the items. All we need to do at that point of time, just do a lookup and get the relevant embedding. At that point in time, this is very fast. And then we retrieve the top K candidates from the ANN index. So the ANN index we already created in the offline steps. All we need to do is take this embedding that we have created, query the ANN, get the top K retrieved results. So we would have ANN results for user to item or item to item. So that would be the next step. Once we have queried, let's say we get back like 500 to 1,000 candidates. So now imagine we had millions of items. From that, we have now reduced it to 500 or 1,000 candidates that we have available. Generally, the goal of the retrieval step is all about recall. We want to include the right items in that 500 to 1,000, but it's okay if we don't get like just the right items. It's more important to cast a wide net and get as many good items as possible relevant to the user at that point of time. Then we move on to the ranking stage. In the ranking stage, we are going to add the features to the candidate set. We'll enrich each candidate with the detailed features. So we would have the user item interaction history, contextual features, time of day, device, item popularity, recency, quality signals. We'll use all these different features that we had pre-computed in the offline step, connect them to the user and the item that we are looking at that point in time. See, we have those 500 items that we have and we have the user. Connect all these features back. We use all these features eventually to use this ranking model that we had created and rank the top K candidates. Now that we run our sophisticated ranking system, we score and sort all the candidates, and then we return to the user about 5 to 10 results. So what you see in your because you liked X, you check out Y, there is this entire process that has happened in the background to get you the most relevant items for you at that point of time. This step, the ranking step, is all about precision because we have a small set. We can afford to do an expensive computation at that point of time. We only need to rank 500 to 1,000 candidates at that point of time. The genius of this design is speed. Retrieval handles millions of items in milliseconds because it's working on vector search. Quality, ranking uses complex models on a manageable set. Scalability, most of the computation happens offline. And flexibility, it can mix multiple retrieval strategies, swap ranking models. So that ways, this entire architecture helps us manage the scale of this problem at the latency that we need to achieve. So this is the architecture that we will be implementing in the tutorial today at a much smaller scale. Um, Retrieval with embeddings and FIS, which is one of the libraries for vector search, and then ranking using LLM reasoning. Before we get on the hands-on part, let me explain how embeddings actually work. So we mentioned embeddings here and embedding models. So let's get into what embeddings actually are. Embeddings are the secret sauce that make modern recommender systems scale. Here's the core idea. We convert the items and users into a dense vector representation in a high dimensional space where similar items are closer together. So for example, in this example itself, you can see that let's say man and woman are denoted by these numbers. And then when you look in this vector space, they would be closer together because those words are semantically similar. And similarly, like king and queen are going to be closer together because those words are semantically similar. So when you do a cosine similarity between these vectors for these words, they would be closer together than they would be to other words. So that is what embeddings actually are. A fixed size vector that captures the semantic essence of an item. For movies, for example, that might encode the genre, the style, the mood, era, what sort of movie is it. All this would be compressed into a single vector. We have embeddings for everything. We have embeddings for text, we have embeddings for images, we have multimodal embeddings. There are pre-trained models that are available on Hugging Face that you can go and look at right now as well, that can help you embed like any sort of information that you can provide. There are video embeddings available as well. Why this solves the scalability problem? Because once we have embeddings for any item or any user, we just need to do a simple vector similarity computation. Instead of 100 trillion comparisons, we can use specialized data structures like nearest neighbor in milliseconds. So this is the foundation of modern retrieval. Now let's see how we can make it fast. So even with embeddings, we still have the challenge. Given a query vector, how do we quickly find the most similar vectors among millions of candidates? So how does approximate nearest neighbor search work? The problem, we will start this by motivating what the problem is. The problem is that computing cosine similarity between a query and 10 million items still requires 10 million distance computations, and at query time, that's too slow. The ANN solution is we trade a tiny bit of accuracy for massive speed improvements instead of finding exact neighbors. Like if we want to find the closest item to this item, that would be difficult. But if we can trade some accuracy for some speed, that is where approximate nearest neighbor search comes in. So let's look at this specific algorithm that will kind of give you an idea of what approximate nearest neighbor search is. So let's say we have all the embeddings and all the items. We'll run a k-means over it, and then once we have the clusters, we are just going to index it. So the green cluster, the yellow cluster, the pink cluster, and the gray cluster, we will just store the centroid for all of them and all the vectors that should be going into that cluster. At query time, what we are going to do is we are going to take the query data point, only compute cosine similarity to the cluster centroids, so that we know, okay, which cluster does this point actually fall into. After we have done that, we know, okay, this query point should be closest to the yellow cluster, and then we are only going to compute similarity with the yellow cluster. So now you can imagine that if we had 1,000 clusters, we have reduced the computation size. We have divided it by 1,000. We are checking that many less data points. So this is what approximate nearest neighbor search is, and this is how it helps us reduce the computation cost that we would need to do otherwise. Now that you have understood the retrieval side, let's talk about how LLMs enhance the ranking side. So this is the whole picture of what we are going to be doing in this hands-on tutorial. That's called zero-shot re-ranking. So in the retrieval stage, we are going to generate text embeddings using movie titles and genres. We are going to build an FICE ANN index using those embeddings. We are going to retrieve the top k nearest items. So if you liked X, here are the similar items based on the embedding proximity. After that, in the ranking stage, that's where we are going to bring the LLMs in, and we are going to re-rank the retrieved candidate set that we have generated. We can provide it anything about the user, right? Like we can provide it context of that time. This user is looking to watch some Christmas movies, let's say right now, given the season, or we can provide it more information about the user, like they like animated movies, or they like movies about pets, something like that. We can give it more information, then allow the LLM to figure out of this 25 items, let's say, what is the best thing to show to the user at that point of time. So this is what we are going to build today. So now let's go to the notebook. So if you, okay, I can help you. If you can go to the PyData Boston schedule, you should see the notebook link there. Now let's get started with the notebook. So we're gonna first quickly just download all the libraries that we are gonna need in this tutorial. The API key that is there will not work because I revoked it. So use your own API key. Okay, just go ahead and start downloading all the libraries. It'll take a minute or two, and then you can import the libraries. We are going to be using NumPy, Pandas, Matplotlib, scikit-learn, FICE, OpenAI, and sentence transformers. I think you might have heard of most of them. If FICE is new for you, that's the one that we used for the vector index. So the approximate nearest neighbor search, that's a Facebook library that they have created. And then sentence transformers is something that we're going to use to get the embedding models. So the word embedding models that we are going to use. Yes.
Show us how you put the cat on there.
I think you helped me do that. No, I don't remember. Okay, once you have your libraries imported, so I told you earlier to save your API key into a notepad. Go ahead, run this cell, and then it'll allow you to put your API key here. So you can put the key here. Moving on, we are going to download and load the movie lens small data set. So this is a data set that contains movie information and user ratings. We'll prepare this data for our recommender systems. But to download this, just run this cell, and then it'll get downloaded in your Colab environment. Once you've downloaded it, click on this folder icon on the left, and you should see an ML latest small here. Okay, so if we start exploring what this data set has, you can see there is a movies.csv, there is a ratings.csv, tags and links. So if you also run the next cell, that will also tell you the same thing, what all is there available in this data set. So MovieLens is a very common recommender systems data set that's used in academia generally. They have a lot of different versions. So this is the smaller version that we are using for this notebook right now. So we can explore a little bit more what is available in this data set. In the movies.csv, generally you'll find the movies, the titles, and the genres. In the ratings, you're going to find user movie ratings. So any particular user that has rated any particular movie, that is the information that you should find in ratings.csv. Your task for the next cell is to just read the CSVs like movie.csv and ratings.csv and inspect how many rows are there in each file and display the first few rows to understand the schema better. You can read the pandas documentation in this link to figure out how to load the CSV files and figure out how to check row count, etc. If you have any questions about this, please raise your hand. We'll come to you. How are we doing with this step? Can I get a show of hands for whoever is done? Okay, everyone's done. So we have about 9,742 movies and about 100K ratings available for those movies. Are you all able to see what the data set looks like? Okay, nice. So let me just put the results here as well. You might have the answers as well, so you can check that too. And then have movies.head. So this is what the movies data set looks like. You can see the titles and the genres are separated by a pipe. And we have like multiple genres that a movie can possibly fall into based on this data set. And then for the ratings.csv, oh, did I not load it? Oh, sorry.
You just run this control and you just run the cell.
This is what the ratings data set looks like. So you can see there's a user ID and there's a movie ID. The movie ID corresponds to the movie ID in the movies data set. And there is a rating that the user has given to, to each movie, to different movies, and then there is a timestamp that's available. We can move on to the next step. We'll be cleaning the movie metadata. So you need to replace the genre separators with commas for readability. You can use the pandas string methods to learn how to replace characters from a text column. And then we are going to rename the columns. We are going to rename movie ID column to just ID and then genres to tags. So you can go ahead and do that and read the docs. They should provide you some tips for how to do this. I'll give 2 minutes. I'll just put the answers and
try to do it.
feel free to take a look at that. So you'll just use the string replace function from pandas string documentation, and then we are going to use the rename function from pandas as well to rename the columns. When we run this cell, we can see the columns are renamed, and we have commas here that allows us to deal with this data set a little bit better. We'll do some exploratory data analysis in the next step of this data set. We generally do EDA to figure out different things about a data set, generally the distribution of different columns. We often also try to answer some questions like how many movies have been rated more than 100 times, what is the median number of ratings per movie, what is the distribution of the rating count. A lot of times in recommender systems, we see that there is a lot of popularity bias and the data is very skewed. So taking a look at these sort of questions will give us an idea of what the data looks like. So go into like these documentation links and try to figure out how you can get the answers to these questions. In that case, you guys can maybe shout out and let us know how many movies are there with more than 100 ratings.
134.
134, okay, yeah. And what's the median number of ratings per movie?
3.
3.
Okay, nice. And if you have also figured out which movie has the most ratings,
Forrest Gump.
The reading number.
we'll give a minute for everyone to.
The one with the fewest should be something you've never heard of.
Yes, hopefully. that should be the case, yes.
When night is falling,
That's fair. I haven't heard of that one.
then it worked.
Yes. Okay, so here are the answers. Basically, we would be grouping by movie ID, and then we can get the size. That gives us this data set which has the rating counts. So how many times was each movie rated? Then we can do this, which basically takes the rating counts and gets us all the rating counts that are greater than 100. That gets us the total number of popular movies, and then we can do a median over rating counts to get the median number of ratings per movie. And we run this, we can get number of movies with greater than 100 ratings, 134, and median number of ratings per movie is 3. We can use this function index max to get the movie that has the highest ratings in this data set. That's Forrest Gump.
The ones here, like maybe $5 or so. Oh, okay.
Moving on, we also want to just see the distribution of number of ratings per movie.
Yeah,
So
it's like, even if
once you've computed the rating counts for each movie ID, you can visualize how frequently movies were rated using a histogram. So go ahead and take a look at some of these docs that have been linked to find out how you could rate this, how you could plot this data frame, and yeah, should be a simple function. Basically, pandas provides us very handy functions to do plotting as well, so we could just directly use that. And here we can see the distribution of movie popularity, and we can see that most of the movies have not been rated before, and there are a few movies that have been rated more than like 200 times or 300 times as well. So that can kind of show us that there is a very few number of movies that actually are very popular, and most of them nobody has probably heard of or nobody has rated, right? So this is a extremely skewed distribution. So this is something we see in recommender systems often, and this also creates this popularity bias problem that we often see in recommender systems, because very few movies actually have any interaction data available for us to use that interaction data to show those movies to other people. That's why content-based recommender systems are still useful, and that's why we have to kind of create these hybrid systems, because if we just use collaborative filtering, we might not have interaction data available for a lot of movies, and hence we might not be able to recommend those movies to anyone, which would keep propagating that popularity bias again and again and again further on. Yeah. Okay, so
have
now sorry, yes.
Sorry, and under this hybrid system that we're building,
Yes.
we're sort of propagating this bias, right? Because we're filtering out only the most rated, you know, the
Yes.
movies that haven't been
Yes.
rated.
So for now, like for the sake of this notebook, we are just going to filter out the top movies and then get results from that. But a lot of times there is a lot of noise in the long tail as well. So we might need to do some level of filtering there. But we would not generally be doing. We wouldn't just generally filter out everything. This is just for the sake of this notebook
Okay,
and
so,
for the sake of this tutorial.
so not all hybrid systems have this problem.
I think like the problem would exist to some extent because it's not possible to just like get rid of popularity bias as a whole, but there is lots of methods that we use to improve diversity in the system so that we are at least showing the middle of that tail, if not the whole long tail. Because the reason the long tail is not showed because they are not very popular and hence they might not get that much engagement either, right? So if any recommender system keeps showing you things that nobody is engaging with, the company would suffer and the users also will not enjoy that experience. But we want to kind of make sure that we are not just showing just the most popular movies, but like also showing a little bit more of that range through some diversification methods that are available.
Have a wild card draft system or something?
Um, there are like experiments in which we have like a PE persistent experiment that's always running, where we would be showing like somewhat randomized movies to kind of understand what happens, right? And do these movies get engagement if we surface them? Because a lot of movies never get surfaced, hence they don't get engagement. But if we have like a persistent experiment with random movies to like let's say 10% or 5% of the audiences, do they get that engagement then? So if they get that engagement then, that allows us to get more data about them and that allows us to show them to more people over time. So yeah, there is some amount of like randomization that's done to the data to achieve that as well. And there are other diversity improving techniques as well.
Maybe.
Okay, so as we have discussed, this is something we are doing for the sake of this notebook to reduce some noise in the data. We will just filter the items data set to keep only movies that have been rated more than 50 times. Yeah, so you can look at the docs to figure out how to do this. If you have already done this, please do shout how many movies are there in this data set. No, okay, wait.
BM,
134?
like this.
No, that was for 100, when we are filtering with 100 rating, right? Yeah. This is the next step.
436.
I think it's M.
Okay. 436. Should be 450.
Yeah, 50.
450? Okay.
Okay, I think it's working on it.
Might have a greater than instead of greater equal.
Okay.
Yeah.
Yeah.
Yeah. It could be just.
Try doing my dash scripts.
Okay, to get the popular movies, essentially we can do this sort of filtering and then we can get the index of these and that index can kind of help us get the right items.
I see.
And then we can use the isIn function, which is one of the string functions in pandas, and then we can use that to filter out only the movies that are there in the popular movies variable that we created. We can also reset the index if you want to do that. And when you run this, you should see that there are about 450 popular movies, and this will also show you the top movies. We have seen this data set before, so it looks similar. There's titles and tags. Okay, moving on, we are going to get into embedding the movies finally. You can read a little bit more about word embeddings here. Since I've already discussed it, I'm not gonna get into it again. Sentence transformers is a transformer-based um, model optimized to create embeddings for whole sentences or short documents. It captures the meaning, the context, and semantic relationships, making it perfect for tasks like search, clustering, and recommendations. I have written here that we are going to use this model, but if you want to use any other model, also feel free. Go to the sentence transformers link here, check out the different models. This is one of the models that has an embedding size that's a little bit manageable. It has an embedding size of 384. Compared to some other models, they have a little bit of a bigger embedding size, so that's why I decided to put this one here. But if you want to use a different model, please check out the link and see the different models. So in this task, basically you have to initialize the sentence transformer model, and then you have to complete this function using which we are going to encode the text. So you can imagine that some text information is going to come into this function, and we are going to encode it using this model that we have initialized. Yeah, this is how you get the dogs and the other things, in case anyone wants to put that too. So basically, you go to your settings, go to miscellaneous, and you can add everything. Okay, since we have 15 minutes left, I am going to move on and show you the answer for this one faster. Okay, so essentially you can just like call the model using this command, and then you can just encode the text and then convert it to NumPy. We have to normalize the embeddings at this point. By normalizing the embeddings, what happens is it creates a unit vector. That ways, when we are doing the cosine similarity, it becomes a dot product. So just run this, it'll load all these different things that it needs to load. These models use a lot of tokenizers and other text transformation techniques. So it loads all these different things, and then when you run this cell, you can see that, sorry, I need to print this. You can see the size, you can see the embedding, and then if you want to see the shape of this embedding, that is also something you can see. So you can see here that the shape of the embedding is 3,34, 3 because we have 3 movies, 34 is the size of each embedding. So that's the dimension of the embedding. Moving on, now we are going to generate the movie embeddings. We are going to use the function that we just created. We are going to pass the titles and tags from the data set, the movies data set, the items data set that we created to create these embeddings.
Z-scaler.
So we can simply do something like this to create the texts. There is like very simple ways to manipulate data with pandas. And then just use this function as it is.
But because you're not able to log into your
How are we doing?
Aren't they already normalized here?
They are already normalized here, actually, you're right. I think I just added an extra step. So I don't think we need to do this here again, because we did it in the previous step. So when we run this, we'll be generating the embeddings for all the movies in the data set.
There's like a normal one. Well, no, I know that, but like.
And when you print out the shape, then you should see 450, 384, because we had 450 movies, each of them having a dimension of 384. Good. Yes.
Does the data set have a synopsis of the movie? Because that might be a better description for
Definitely.
matching than.
Definitely. I think like, so this data set does not have that.
Okay.
But when we are creating an actual recommender systems, we use a lot more features than what we have used here. We have only used genre and like some title. The title doesn't have enough information about the movie for us to really know what the movie is about. But in a real use case, we would be using some sort of a description, maybe an image, maybe we would be using the people who are in the movie, the directors and other things, and that would really make an embedding that contains a lot more information can be used better for similarity search. Yes.
Would you ever use language from the ratings themselves? So like rather than just like an impression of whether they liked it or not, like maybe why they liked it and like the actual content of their rating.
You would use the rating itself in collaborative filtering methods. You generally filter out the movies that are poorly rated. That way you get the positive signal. You can use it for positive and negative, right? Something's been rated poorly, that means that's a negative signal, and something's been rated positive, well, that's a positive signal, so you can use that. Why they specifically like something is generally not available. In a recommender system, you only have like, okay, did somebody click this? Did somebody purchase this? So you only have like binary signals available. Yes.
I have a more general question, which is we're building an embedding on the title and the tags, which are both item features. They're not like user-related features.
Yeah.
So why do we filter out like only the movies that have more than 50 ratings or something? Because we don't really need the ratings, right? Because we're not doing any kind of collaborative filtering at this point.
We have just taken the top movies. We are not doing collaborative filtering in this one as of yet, but in the LLM based, we are not going to be doing collaborative filtering, but we are going to take user context into picture at that point of time. Yeah, we are just filtering those out to remove some noise,
Okay.
essentially, not necessarily to use the rating itself. Yeah. Okay, so if we are done with this step, you should technically see the embedding shape 450 into 384. Now we are going to get into building the FICE index. We have talked about what vector indexes are. FICE is Facebook AI Similarity Search. It's a high-performance library for nearest neighbor search that is used in production applications. Because it's optimized for large data sets, it supports CPU and GPU acceleration, and it has many types of indexes that it can create. You can create flat indexes, or you can also create hierarchical indexes, or you can do the k-means algorithm that I showed earlier. That's called IVF. In this notebook, since we only have 450 movies, we are going to create a flat index. By a flat index, I mean you're going to have the similarity between each movie, and you're going to just use that. You're not going to do like a k-means clustering beforehand. Oh, sorry, I was moving the wrong one. Yeah. So moving on, here you can check out some of these docs to create the index flat IP. You will have to provide it the embedding dimension. So we just discussed what the embedding dimension was in the previous step. You can provide it that, and then you will have to create a FICE index. I'm gonna provide the answers here. So when you do the shape, you can get the embedding dimension. And when we create the FICE index, we just need to call this function, then we need to provide it the dimension, and that helps us create the index itself. You can run it, and then you'll see the number of vectors in the FICE index. Basically, at this point, it has created an extremely optimized performant index, where if you pass one embedding, it can get you the closest results. And then let's get into the retrieval function. Basically, now that we have created the index, the only thing we need to do is query the index with the movie that we, like, let's say you as a user like Toy Story, or you like Forrest Gump. We are just gonna index the embedding for that movie. We're gonna pass that embedding to the ANN that we have just created, and that's gonna give us the top K results. So that helps us create the retrieval function. This is how generally also retrieval functions are created in production applications, just the scale is much smaller here. So we'd have to reshape it, and then we just need to pass it to the function that we created, to the index that we created. We use this function .search. We are going to pass the query. The query is something that we got from here. This is the embedding. And then, yes. And then we can get the top k. K is a parameter here. And then we just run it. And we run it. That is our retrieval function, essentially. And we can see the results here. For example, if I want to see the results for Toy Story, I can get the index and retrieve similar items.
Yeah, like new cell.
Retrieve similar items is the function that we created. We are trying to get 25 results here.
Click on this.
If we run this function,
Yeah.
sorry,
Add code.
this should be
Rename it
movie
Toy Story.
index. That's my bad. You might need to correct. Yes. Movie index. And this will kind of give you the top 25 movies that are similar to the movie that we had selected. You can try putting a different movie there and see what are the similar movies to that. Now you can see that the movies that is showing is also Toy Story, Toy Story 2, Toy Story 3, and Toy Story 4. Why does it do that? Because the only information that you have provided to the model is the name and the genre. And all these movies have a very similar name and they have a very similar genre. But if you provide, let's say, the description, the actors, other things, it has more information to do a better job. Now, given that we can see here that this doesn't actually have enough context about the user,
All these files.
that is where the LLM bit comes in. And basically, we can provide, let's say the user likes animated movies or they like some sort of user context. You can provide it in a prompt way, and you can provide the things that have been retrieved. We have 25 movies, and that allows us to get a re-ranked result. So I'm just gonna
That's basically change directory and then
copy paste this here. So what we did here is we took the items that we had, we joined them together to create a natural language, to create a sentence out of them, and then we pass to the LLM all that information. So for example, we have some sort of a user profile. They like pets, they like animated movies, and we have the retrieved items. Then we can ask the LLM, give 2-3 recommendations with short explanations, beginning with because you liked X, you will like Y. And when we run this creates a function. Now let's say our user profile is enjoys animated Pixar movies and movies about pets. This will give us the LLM based re-ranked results. So this is where the LLM recommendations and the knowledge that it has comes in. This is zero shot, so we haven't even given the LLM any sort of like instructions about how to approach this. So for example, they're saying that these are movies that they would recommend. Because you liked animated Pixar movies, I would recommend Toy Story, Toy Story 2, and Toy Story 3. So this is very similar to the results that we got from retrieval. Those were the top 3 results that we got from retrieval. But they also said because you enjoy movies about pets, this might also be a great choice. So it'll also recommend things, it'll take the user's context into consideration and also recommend things that are relevant to the user at that time. Then it also recommended another Pixar movie, which is Up, which is also related to pets, and that kind of takes more of that user context into consideration as well. Let's say somebody enjoys like love stories, you can change the user profile and the user context, and you can play around with this in your own time, like change the context, change the initial movie that you started out with, and see how the LLM recommendations are different from what is being recommended just using the retrieval candidate set that we have. So for example, if we said that, okay, this person enjoys love stories, we have some more context about them, then it's going to recommend things like Beauty and the Beast, The Little Mermaid, Up, which are related to the initial movie that we had, which was Toy Story, because they're animated, and that's, we have used the genre in the embedding, so that's how they are similar. But they are also love stories, so it has kind of taken the user profile into consideration. And we are done. Yay.
And of course to Chicago, and let's clap for her. Yeah,
Okay. We are at time, but if you have any questions, please shout out. Yes.
Sorry, so the last two examples, are you still feeding in any of the vector search stuff to that, or is it really just that description about the user?
We are feeding the retrieved results. So you saw that we got some 25 retrieved results from the vector search.
Right.
We take those results and then we feed those and we feed the user profile.
Okay, it's all
That
part,
is, we
all
get,
in one big prompt.
yeah.
Okay.
So that allows us to use both retrieval and ranking together.